y'all, it's Jason. Welcome back to another edition of Quarantine Science. I'm just going to stick with that name. I like it better than Sweatpants Science. Plus, if you're wearing sweatpants right now, you're insane. It's too hot. Take them off. Put on some shorts. Anyhow, today we're going to delve deep in my brain. Not really. It's figuratively, not literally. We're going to see kind of my thought processes. Thank you, ADD, because this is what happens when I have way too much time to think about something, which is usually about 3 seconds extra. I don't take any medication, as you can see, and this is why we have a wonderful video today. Today's video is actually just a random thought that I had when I was sitting at my desk at work, but all of a sudden I had that squirrel moment, and that was, I wonder what gravity on flat Earth would look like. Now, in order to get into this, let's go with what we know about gravity and what's been scientifically accepted, I guess, and perfected over the last 400 years, going from Newton all the way up to Einstein and his greatest blunder. So, what is gravity? Gravity is a field. How do we experience this field? We don't see field lines, we don't see gravity, but we do feel its effects. We feel it in the terms of forces and acceleration. So you're probably wondering, I've got my friend Sticky here. He's going to help us figure out what's going on with gravity and help you understand a little bit about spherical Earth gravity and expand our minds into flat Earth gravity. Now, when we're thinking about gravity, we tend to think of the force due to gravity, which is the equation here. So this here is the force due to gravity is going to be the gravitational constant, Einstein's blunder, times the mass of the big object, times the mass of the small object, divided by the distance between the two objects squared. Now, what does this really mean? The force due to gravity is dependent on two objects. The other part of this is that distance thing. It falls off exponentially. It decays quite rapidly as we move away from whatever we are experiencing. Today's topic is going to be looking at more or less not the force due to gravity, it is, but we also need to establish the acceleration due to gravity. And we know the acceleration is just a change in velocity. And we think of acceleration here on Earth due to gravity, the numbers 32.2 or 9.81 kind of pop in your head. But all it is just saying F equals ma. We're going to take that force, we're going to divide it by m, which you can see here that we're left with gm over r squared. This equation really depends only on the big mass of what we're falling towards and our distance away from it. It's independent of the small mass. And this is where we say in a vacuum, I'm going to asterisk that, in a vacuum, a feather and a bowling ball will fall at the same rate because it's independent of that mass. When we're looking at it as a far field, near field equation, we see that in the near field, we not only have a downward pull, but since our mass is spread out, well, so are the forces. Now all of a sudden we're having forces that we don't really perceive, but are pulling us at angles. So there may be, because there's mass to one side of me, there's also mass to the other side of me. The nice thing about spheres is it's relatively equal from one side of you, left side of you, to the right side of you. So you don't perceive that force because you're being pulled equally in both directions. And we can kind of look at this in a vector math sense, where if we are looking at a force, let's say you're pulling a sled by a rope, you're pulling at an angle as you pull the sled, but part of that is a component force that's pulling that sled up, and another part that's pulling that sled forward. And we're going to look at the horizontal forces and accelerations of flat Earth gravity. So on spherical Earth, those accelerations and forces will equal each other out in a horizontal sense, and then you're just left with the force that's pulling you down. Well, on flat Earth, well, things change. Now, if you're standing at the center of flat Earth, we'll call that Null Island. Here on spherical Earth, well, Null Island is a marker in the Atlantic Ocean that signifies the crossing of the prime meridian over the equator. So we're going to use that as our starting point. That's going to be our null point, or Null Island, as they call it. And then we're going to unfurl Earth. So we're going to unroll it. That means that the circumference of Earth now becomes our diameter. And, well, with that, we want to maintain our mass. We're going to try to simplify things. So we're going to keep the mass of flat Earth equal to the mass of spherical Earth. And then we're going to go with a uniform thickness. Everything is kind of the same in a downward sense. I say kind of because now our radius moves up to the center of the mass of flat Earth, which would be the center of the circle if we were to look at flat Earth from top down. But in flat Earth, from looking from the side as you see here, well, it would be in the middle from the thickness standpoint as well. Well, that radius shrinks, and remember what happens when that radius shrinks? Those numbers on top get really big. So there is going to be a change in a vertical sense of that force and acceleration on flat Earth. But what becomes really kind of interesting, really cool, is that horizontal component. Because if you're standing at Null Island on that buoy, you do have equal mass from left to right of you. But when you start moving away from Null Island, guess what happens? We can see in the vector math of these forces pulling you left and right that you do wind up with an imbalance. So you no longer have equal forces pulling you left and right. Now you have some kind of force pulling you towards Null Island. So here's an illustration. Sticky's riding on the blue line. Null Island is right there on the yellow line. And for this math, what I did is I broke out the Earth into 3 segments. So the red line is just the equal distance from the blue line to the yellow line as the red line is to the yellow line. And the way I conquered this math is I actually came up with an equation using calculus to be able to figure out the mass of the center portion of flat Earth as you move across flat Earth, as you move away from that center. Well, we're going to subtract the part that is going towards the edge away from everything else. So everything that is on the side closest to me of that blue line, well, we're going to subtract that from that far side. And we're going to see what happens mathematically. And you see here what's happening with that gravitational force or the acceleration due to gravity. You see that our R's and our M's will actually shrink or increase in size based on their numbers. And as you see Sticky writing it, well, the mass of the that smaller portion gets subtracted out from the mass of the bigger portion, but that radius almost stays a little bit the same, and the mass from the larger portion will fall off. So then we're left with this really big equation. This is ugly. How ugly is this? I mean, this is the equation for the force. Now, if you want the acceleration, which is what's in the chart over here, uh, you just drop off the m in the front of that equation, and then you'll get the acceleration. Here in the chart, though, the red line represents that vertical force due to gravity, actually the vertical acceleration due to gravity. It's at 9.81 meters per second square. That's just something that gives you good reference. And you see the yellow line, that's that acceleration in a horizontal sense towards the center of flat Earth. So as you move away, what's occurring with that acceleration? Well, at first, you shoot all the way up to 3 times what we experience here on Earth. At about 300 kilometers, it reaches that maximum where it's 3 times what we would feel here on spherical Earth. And as you move further out, it decays, and this is where that radius becomes greater and greater, much more so than the mass, because as you're moving away, the amount of mass that you're adding to the left of you as opposed to the right of you, or what's behind you, what's pulling you back, that mass, the addition of that mass is getting less and less, but the radius from you, or that distance from you to Null Island, is increasing. So there you have it. Thank you, Sticky, for sticking around and bearing through this with me. And I hope you've enjoyed seeing what flat Earth gravity would look like. Just so you understand, if you're on flat Earth, you get pulled probably at some point more so in a horizontal sense than you do in a downward sense. And at the end of the day, what would occur is that anything that's not nailed down, that is rooted firmly into flat Earth, would all fall towards the center, and it would make one big sphere. So there you have it. Flat Earth would probably just decay back into spherical Earth. Sorry, if you like the flat Earth theory, gravity is working against you. Gravity on spherical Earth works against us all, but that's a different story, and that's a whole lot of biology. Oh, I did want to do one experiment. Back. The one experiment. There you go. That should tell you whether you live on flat Earth or spherical Earth. Enjoy. Like and subscribe. Hit the button below. Thumbs up. Smash it if you so desire. If you do, I won't be able to tell if you smashed it. But if you did, just put it in the comments below. Say you really liked it. Otherwise, I'll catch you on the next one. See ya.